Hi there, physics students. My name is Eric. I'm a VIT qualified physics teacher and tutor at Complete VC Education. And today, I want to walk you through this Unit 4 area of study on SAC. And in the meantime, give you some tips and tricks and also walk through the minds, of teachers when they draft this SAC. So the questions and solutions are written by Raw 50 tutors. And my job here is to walk you through the basics of it and also share some insights about how to do questions effectively because it's a 90-minute SAC, which is very, very lengthy. And many students will find themselves to be lacking time to complete the whole examination. That's one thing. And the other thing is any tips and tricks, right, to do the SAC effectively and to save some time here and there. So I'll go for some insights that we gathered from the last year's mock exam paper. In fact, it's the 2024 exam paper in VCE. There are several things the examiners pointed out, and that requires immediate attention. So without further ado, let's dive into it. There are two sections to the SAC, which is very similar to the mock exams in the actual VCE. I usually recommend students to do section B first because for each question, they're worth more marks. And it's just like spend the time wisely, right? It's more cost effective to do the section B questions first because for section A, you can see each question worth 1 mark. And for each question, you can see it's quite lengthy. It requires a lot of thinking and it may take you 2-3 minutes to think in one question. So I will leave this till last in usual cases, but for today's walkthrough, I'm going to show you the multiple choices first as a brain teaser. Okay, so let's kickstart today's explanation. Question one. Question one, it's a continuous transverse wave. So as I read the question, I'll highlight the important parts. It's a transverse wave showing at instant time. The wave moved from left to right at a frequency of 2 hertz. Right, so the first information we got is f equals to 2 hertz. Immediately, I'll figure out what the period is, which is 1 over f, right? And that's 1 over 2. In other words, it's 0.5 seconds. You can do it in no time. And as you read the question, it's asking, okay, if you place an object, a cork, at point P at the instant shown above, right here, where would it be 0.25 seconds later? So your job here is to translate that 0.25 seconds into the period in terms of period t. And 0.25 seconds is in fact half the period. So in other words, you're asking, after half a period, where's the location of particle at point P or any object that's placed at point P? A common mistake is people thought that this object travels along the wave, so it could be S or it could be T. But in fact, we can eliminate these two options immediately because we know for the fact that for waves, it's the transfer of energy without the net transfer of material. So in a transverse wave, the motion of the wave is, let's say, to the right-hand side, but the particles only move up and down, which leaves us to the option Q and R. Now, if you think about point P, it takes 1 period to go to the bottom and go back to the top, which means it takes half the period to get to the top, to the bottom of this wave, right? So in fact, R is the answer for question 1, that's B. Question 2, this time we got a standing wave, so it's important to distinguish which wave type it is. Fixed at both ends, that's the only type we're going to see in VCE from now on. The length is given as 4 meters, so let's jot it down. L is 4, and the speed of the wave is 5 meters per second. That's V. And at the instant shown below, the standing wave is at its maximum point of oscillation. So it's the maximum displacement at all points. After 0.3 seconds, which of the following depicts the waveform? Okay, so when you see standing wave, there are equations that's not given in the VCAR cheat sheet. So you're going to put those formulas in your own formula sheet. So there's two, which one is lambda is 2L over N, and consequentially, the frequency would be NV over 2L. Okay, so we got two. Of course, there's another one. You can say the period instead is 2L over NV, right? That's 1 over frequency, so you just take the reciprocal of the fraction. In this case, let's see. Once again, we try to find a period, right? Because we given the time, it's given, so you can express this time in terms of period, a similar way to think as question 1. So period is 2L over NV. You put the values in, 2L. Now the tricky thing is, what is N? All right. And in fact, this diagram is not perfect. I will actually do one thing as we go, is I'll just sketch the dotted lines as well. Because we knew for a fact that it's a standing wave, right? It's not a traveling wave, which means that we have notes and antinotes, right? The wave kind of stands still or oscillates at its own place, right? And then we count the number of loops, right? So there's 1, 2, 3, and 4, which means N in this case equals to 4. There are 4 loops presenting in the picture, which means they got 4 times V, which is 5. And this becomes a very easy question to solve, right? That's 0.4 seconds. And 0.3 out of 0.4, right? The fraction is 3 out of 4 of this period. Okay, so if you think about, let's say we got a particle at the first loop, let's say at the very top, the particle is right here. It takes a quarter of period to move down to the equilibrium position. It takes another quarter of a period to move to the bottom. It takes another quarter to move back to the equilibrium position. In other words, we'll have a waveform like C, because if I just draw the whole instance, right? So that's the first, at t equals to 0 period. At the first quarter, I should say, right? It becomes like that. At the second quarter, right? T equals to 2 out of 4 period. It looks like this. And then 3 out of 4 is just like a flat line. Okay, so therefore we have a diagram looks like C, it's sort of like still at that instant, but in fact the wave is moving. It's a standing wave. All right, and the better way to put it is all the particles are at the equilibrium position at that point. So that's question 2, C. Question 3, please train yourself. Whenever you see the word diffraction, and in fact there's only one formula that dictates diffraction, okay? There's only one formula. That is the diffraction degree is proportional to wavelength over the width of the gap. Okay, so this is a formula we use every single time when we talk about diffraction in VCE physics. So doesn't matter what question it is, I'll always write down this formula. We can do DIFF, diffraction is proportional to lambda over W, that's fine. And if you check the numbers right here, we have the wavelengths given, we have a gap width given. So asking which one's producing the greatest diffraction. So you want to get the greatest ratio, right, for lambda over W. Some of you may ask, Eric, do we need to convert the units? Because I see there's nanometers, there's micrometers. But hey, if all the units are the same, right, so all nanometers, all micrometers, there is no need to change the units. Okay, you simply use the same set of units, right, for all the calculations. So for instance, the blue light is 450 over 0.3. And then you have what? You have next one, 540 over 0.4, and so on and so forth. Right, 680 divided by 0.6. And you simply compare the size of these ratios. If you put the numbers in calculator, you get the first one as 1,500. Second one should be this, and then 1160, and then afterwards 1137-ish. Sorry, double threes. And so in conclusion, the first one has the greatest ratio, and which means they have the greatest degree of diffraction. So the answer should be A. For 4 and 5, we use the same prompt. Okay, so whenever you see like a zebra sort of a pattern, right? It's like a crossing. It's immediately you're going to think about interference. You're going to think about light as a wave, or even electrons as a wave, right? And that is the Young's double-slit experiments diffraction pattern, or sorry, interference pattern. Central bright band is labeled as C, which means the path difference is 0 lambdas. The question is asking which one's the closest to the path difference at band X, right? So band X is a dark band. In other words, we have 0.5 for the first one, 1.5 for the dark band. So that's the path difference. What I'm writing down is the path difference in terms of the wavelength, right? And that's 1 lambda. You can put this in. Okay, 1.5 lambda. And yeah, basically, if you can find what lambda is, you solved the question, right? So our job now becomes, what is the lambda, given that we have a frequency, f? The first equation that may pop up in your mind is v equals f lambda. That's the wave equation. But then it is not given the speed, right? It seems like that's the case. But remember, this is light. Light travels at the speed of light, okay? So we can do like this, right? We can do rearrangement. And therefore, v is 3 times 10 to the power of 8 meters per second. That's the speed of light, it's a constant. And frequency is given as 4.8 times 10 to the power of 14, okay? So the wavelength is going to be quite short, right? In this case, let me check. Yeah, in fact, you can put in the calculator, times it by 1.5, and the answer should give you as 9.375 times 10 to the power of -7 meters. Okay. None of the options is exactly like this one because we express the units in nanometers. Okay. So yeah, if you convert the units, 1 nanometer is simply 10 to the power -9 meters is given in the formula sheet. You get C as the answer. Okay. But the idea is you can do some sort of labeling right here to help you to think. Okay. Whenever you got these interference patterns, write down and don't write down n equals to what. Simply put down the path difference is how many lambdas. All right, question 5. Distance between two slits creating pattern would be, so this one you can see the different units. Okay, so straight away, you should have an alarm set up in the system that you're going to convert the unit straight away, right? Distance between the slits is basically d, right? So d is the distance between the slits, right? Because the formula we're using is delta x is lambda L over D, right? D stands for the distance between the slits. So if you can just draw what's happening, I can draw a sketch it right here. That's D. That is L. And then you got some like sort of fringes, right? Different patterns. Okay, so between the center to the other one, that's delta x, right? And there's like a wavelength of light you use, that's lambda, right? All of them are distances. So 40 times 10 to the power of -6 meters, you convert that straight away. Delta x is given the last, right? 3 centimeters means to the power of -2 meters, all right? And if we put all the values in to the equation right here, I'll move it to the side, you got 3 times 10 to the power of -2, and that is equal to the wavelength you found. So let's imagine you simply put the wavelength expression, that is the speed of light divided by frequency. Let the calculator do the hard work, times L divided by 40 times 10 to the power of -6, right? So that's simply algebra. Okay, so you should be very capable in terms of algebraic expressions, make L the subject, and you can find the answer to be 1.92. Okay, the method is you multiply both sides with this number and you divide by this number right here. There you go. Okay, so that's questions 4 and 5. Moving onwards, question 6. I see a graph like this immediately pops up, photoelectric effect. And this word photoelectrons further verifies my hypothesis, right? This is about photoelectric effect. Not to mention EK max and frequency. These things are the keywords in photoelectric effect. Now, 2 things I would definitely do when I do questions like that. Okay, guys, you have to doodle on the worksheet. You're gonna doodle on the exam paper. Okay, don't keep it clean. Okay, keep it have an organized chaos is what I would say, because you overlook things very often. Put a big J on the y-axis because it's not electron volts. You're going to remind yourself that it is in joules, not EV. Second thing, times 10 to the power 14. Okay, because you'll overlook that. You forget that, trust me. As you go into the paper, usually in the VCE, this is the last topic, which means it's question 15, 16, 17. It's hard to keep focus. So you're going to set up systems to remind yourself that you don't overlook these details. Okay. If you analyze the question carefully, I can eliminate options A and B immediately without doing any calculations. And I would say C, is the correct choice. Okay, because if you look into it, what does C say? Any photon that can eject an electron from metal B. Now note that metal B has a greater work function than metal A. Okay, metal B has a greater work function than metal A. So if a photon has enough energy to liberate those electrons, right, to overcome the work function and therefore ejecting the electron out, there should be no issues with metal A, right? So conceptually, this is a correct statement, okay? But it doesn't work vice versa, right? Because if it's enough energy for metal A, yeah, sure, but that's not enough for metal B, or may not be enough, right? So this cannot be concluded, all right? Would it be able? Could be not, right? It's inconclusive, all right? Therefore, the best choice is option C in here. Or look, if you're a man of numbers, you wanna recalculate to see what's going on, you can actually do some calculations. Okay, if you are preferring numbers, you can find out for the work functions of A and work functions of B, right? So the way we do it is we put the values. So notice that actually it doesn't matter which unit is that, because it's like an arbitrary unit. The unit you should pay attention to is this one here. Right. So preferably you use a Planck's constant with the unit EV, seconds, because you can get EV electron volts as the answer. Right. So 4.14 times 10 to the power -15 multiplied by the frequency. Right. Estimate the frequency, that's between 2 and 3. I'd say 2.5. Like a rough estimate is good enough. Okay. We knew for a fact that, look, 4 times 2, I mean, this number should be very close to 10. Actually, you can do the calculations, and that actually gives you 1.035 electron volts. Yeah, a bit risky for that one. Otherwise, you can cancel out, the 10 to the power of -15 and 14, and there's a 10, so you can cancel them out to save you some time. But for this one, look, you just do it in the calculators if you really want to. Just want to show you it is a valid answer. This one's like 5.5. Okay. Roughly 2.277 electron volts. So if you look at the options, 1.7 electron volts, it's enough, right, to liberate electrons, right, to free them from the work function in metal A, but it's definitely not enough for 2.277. Like this number is less than 2.277, right? And so option A is definitely incorrect, whereas 2.5 can cause emission from A but not metal B. This is also wrong because it can cause emission for both metals, right? It's greater value than either one of them. All right. So if you want to do the numbers, you can figure it out. Options A and B are incorrect, and the only option that's right is C in this question. Okay. Now the next one, following situation applies to questions 7 and 8. So let's have a look. It is a current voltage graph. So once again, it's a bolded, right? Which means it's 10 to the power of -6 amps. Make a big circle, make sure it's visible to you. You're never going to miss the detail. Let's see. Which one's the closest to the maximum speed of the emitted electrons? And you'll be like, Eric, like, what about the speed? Like, well, what's the equation relating the two? All right, go back to the formula sheet, right? You can realize that the 1/2 mv squared is equal to QV stopping voltage. Okay, like because the EK max, right, the maximum kinetic energy of those for the electrons being shot out should be equal to the charge of the electron multiplied by the voltage you're setting, right, to stop it. That's why the stopping voltage is a term that we coin for the situation. EK max is like 1/2 mv squared, and the V, of course, is the maximum speed. So we want to find V. That's the quest. Now, unfortunately, I believe you can't use the electron volts value. You have to be, you can't sub in Q as 1 and use electron volts because on the other side, It's like those SI units we use in motion. That's kilograms, meters per second. There's no electron volts in there. And so you have to do it. No shortcuts for this one, okay? Mind you, the mass of electron has updated from the last syllabus. It was 9.1 times 10 to the power negative 31, but now they use like 3 sig figs. So which means all that is updated to 3 sig figs, and that's 9.11 instead. The change should be minimal, but it could cause a slight difference in the answers that you're going to give. Just be mindful of that, okay? Charge is 1.60 times 10 to the power negative 19 times the voltage. Now the stopping voltage is here because when you set the voltage to be negative 2.6, negative because you're reversing it, right? Because you're discouraging those electrons to move across, right? So that's why the potential difference is like on the side where you've got electrons, you actually have like a positive charge right here instead of negative because you want to draw those electrons towards you. On the other side is negative because you want to repel the electrons, hey, don't come here. So it's like a reverse bias, all right? That's what we call them. And that explains the negative. But we don't care. We take the magnitude, 2.6, voila, okay? And lastly, with some algebra magic, you should find V should be very close to 9.6 times 10 to the power 5 meters per second, okay? Now, when you calculate this number, anything that's greater than the speed of light, you should go check your answer once again. And it's not any of the options here, okay? So something you could do when it's like a section B question, let's say, you can, based on the value, the figure and the order of magnitude, to determine if that value makes sense, and you make corrections accordingly. Moving on to question 8, using the same scenario, we're going to continue. This, I would say, is a very hard question, and please put a star next to it, because that's very similar to a question in 2024 VCA exam. Now, a lot of students, they're very good at identifying those keywords. Higher frequency. Eric, higher frequency means higher energy, right? When the incident light has a high frequency, so instead of using like a red light, you use like a violet light, use ultraviolet X-ray, that's higher energy, okay? So definitely the stopping voltage would be increased consequentially. Okay, and they kind of stopped thinking, option C would be the answer because it doesn't mention anything about the intensity of those of the light, so it must be C. If you picked C on that one, okay, you are the target of this question, okay, because there's one assumption we made. The output power is the same, okay? Now this is very, very tricky. It tricks a lot of students, including myself, honestly, including myself. When I first do the question, I sort of overlooked it. Okay, but then after a second thought, I read the answer, I figured out why this is important. Okay, so guys, when you think about the power, you can express it as E over T, right? That's the energy over time delivered. That's the power, right? And say if I have for each photon, we have HF as the energy, and I got, let's say, N photons at the start, right? N photons, right? So NHF over T, that would be the equation. Okay. Now, the thing is, if you want to keep the power the same, so P is constant, NHF over T should be like a constant as well in these two cases. Now you're changing the frequency to be higher. H is a Planck's constant, it doesn't change, which means in other words, N over T, it's something that should decrease, right? To keep this equation balanced, right? To keep P, the power, the constant. Now, what is N over T? N over T is the number of photons per second that's being shot out from the incident light, okay? Now that means if we decrease N over T, we are decreasing the number of photons, well, per second. But guys, can you see that? We're decreasing the number of photons as well. That's a detail you can't really overlook, okay? So even seems like the question says we change one thing, we're actually changing two things here. Okay, not just the frequency, which means it's corresponding to the energy, of course, right? But we're also tampering with the intensity of light, which in turn affects the photocurrent, right? We're decreasing the number of photons, we're decreasing the intensity, and therefore the photocurrent will decrease. There you go. Answer is D. If you get this one right, congratulations. You got a very, very good understanding, spot on, clear understanding to the physics ideas that you've learned. Okay, it's a very tricky question, so congratulations for those who got it right. And I hope we all learned something from here. Question 9. Once again, pattern recognition. Now, what we're doing here is to recognize some patterns. If you look at the options carefully, once again, this is diffraction pattern, right? Diffraction of electrons, diffraction of light. Please write this down. Okay. Now this time, interestingly, is talk about electrons. So we can talk about de Broglie wavelength, or I actually check the actual pronunciation is de Broglie wavelength. Okay. So sorry, I'll just call him de Broglie from this point onward. That's how I learned it. May not be the most correct pronunciation, but here you go. For electrons, we're going to consider this wavelength, right? It's like a hypothesized wavelength. It's as if it has a wavelength. It demonstrates wave properties, despite the fact that it's a particle. Okay, and that size of the wavelength is corresponding to the momentum. Which, in other words, like the diffraction pattern, it's corresponding to h over the width of this like diffraction. So it could be the distance between the crystals, atoms. You know, that's the width. All right, times the momentum, right? So it's inversely proportional to the momentum. So if you want to increase this diffraction diameter, one way to do it is to decrease the momentum or anything associated with it. So greater atomic spacing, okay? When you use greater W, you're actually decreasing, right? Here's another color. If you increase this width, you are decreasing the diffraction diameter. So B is definitely wrong. It's not the right answer here. B is wrong. Okay. If you increase the momentum or increase the energy, guys, these two are the same thing, right? Because energy is P squared over 2m, right? For a particle, you can't use the same formula for photons, right? Because different thing. P squared over 2m for electrons. If you increase momentum, you increase energy. Okay. As I said, when you increase P, it's inversely proportional. So you increase this one, you decrease the diffraction diameter. So these two options are incorrect as well, which leaves option A as the correct option, which makes sense, right? If you think about the voltage, accelerating voltage QV is 1/2 mv squared, right? So big V, capital V stands for the voltage. If you decrease it, you decrease the speed, which means momentum, mv, you decrease the momentum as well by decreasing v, right? So that kind of fits into our discussion framework, right? You decrease the momentum, and thus the diffraction pattern has an increase in diameter. Okay, so it's actually asking a lot of concepts in a single question. So I hope you can draw some connections between the couple points we have here. Move on to question 10. This is honestly a very, very tricky question, okay, that we do. So I hope at this point you realize that the time we spend on multiple choices is way more than a minute or 2 minutes, especially for complicated ones like this, only for 1 mark, right? So definitely you're going to skip it to the end. You do the other questions first in section B before you come back to section A. That's the strategy. All right, number of spectral lines that will be visible. Mind you, we're not asking the number of transitions. Because when we draw the transitions, you can do that, right? That's transition 1, 2, 3, 4. You move on to the second level. So you go from the top to bottom, second and third, and then you go on to the next one, 1 and 2, and then 1. Okay, so there's 4, 3, 2, 1, which means that 10 transitions possible. Okay, but the question is not asking about possible transitions, so don't pick 10 straight away. Okay, it's asking the number of spectral lines you're going to see. Now, the number of spectral lines depends on what? It depends on the energy, right? Or should I say the frequency of the the photon emitted in the process, not electrons, the photon emitted in the process. So it is a very tough task. You're gonna meticulously check to see if the difference, all right, between the energy levels are unique, right? And let's do it, right? You can do 9.4 minus 0, that's 9.4 EV. You can do the same thing for the rest. So I'll just write down the values without the EV, right? You can check yourself. 2.8. This one is 1.3. And then we got 0.1, 3.4, 1.5. That's 1.9. That's 6.6. And this one is 4.7. By writing the difference, so let's say you evaluate differences, you do 6.6 minus 4.7. I do one example for you guys. You get 1.9, right? Electron volts. So that's how we get the differences. And the difference is that the emitted photon, the energy of it. Now you realize, Eric, there's actually two values. They share the same exact value, right? That's 4.7. That appeared once and twice. All right. So even though the transition, we got tens of them, 10 transitions in total, there's 2 of them resulting in the same difference in energy, right? In other words, the photon they emit will have the same frequency, right? Or the same wavelength. And the number of lines would be not 10, but it would be 10 minus 1. That is 9 spectral lines in total. Okay, this may trick many, many students. So be very careful when you see multiple choices like this. Question 11, let's move on. Which one of the following cannot be concluded as a result of the Michelson-Morley experiment? So 2 conclusions for the experiment. 1, aether does not exist. Does not exist. There's no aether. There's no such thing as a medium for light to travel in. Light can travel in a vacuum, nothingness. Okay, they can simply propagate because it's a bunch of wiggly waves changing in sizes, and they propagate each other. So that's a very amazing feature of those electromagnetic waves. Another thing is that the speed of light is measured as the same, it's constant. Doesn't matter which orientation you put the setup in, you're going to measure the same value. So the first one does not require a medium. That aligns with the first conclusion. There's no aether. We don't require a medium for propagation. And B, speed of light is constant in all directions. That corresponds to conclusion number 2, right? Speed of light is constant. Now, aether does not exist, corresponds to 1, but C, it's something true, right? Length and time are dependent on observers, but that's Einstein's special relativity. It is not something that the Michelson-Morley experiment says. All right, so that's question 11. Question 12, speed and Lorentz vector. Okay, this is a math question, honestly, in a physics sort of disguise. If you write down the Lorentz vector, which is 1 over the square root of 1 minus v squared over c squared, you will notice one thing, is when v approaches the speed of light, as you go quicker and quicker and quicker, Lorentz vector would be 10 to the infinity, right? Because if you think about it, when this is c, right, that's c, so it becomes 1 minus c squared over c squared is 1, right? So that's square root of 0, that's 0, so you have 1 minus 0, and that means 10 to the infinity, right? In other words, mathematically, you're going to find a graph that as we have the speed close to the value of speed of light, this graph should explode, right? You should go exponentially high for the Lorentz vector, okay? That eliminates the option of A because it's not a straight line. That eliminates this value because Lorentz factor is going to be 10 towards the infinity as we approach C, not going this like forever. That's false. D is absolutely incorrect. As you go in a greater V, Lorentz factor should increase, not decreasing, which we left with option B. Right, so at speed of light, you see this Lorentz factor is going up 10 tends to infinity. Right, that's the idea. So B is the correct option in question 12. One more to go. Last but not least, for question 13, positron electron, they have the same mass, they collide and annihilate, so which means they become pure energy. Right, so same mass is important. We got 2 times the mass of electron. You can put it down first. It produces 2 identical gamma photons that goes in opposite directions. Closest to the energy of each photon, we want to think about the energy of each photon. So if let's say use E equals mc squared, that's not exactly the true value because it's the total amount of energy for the 2 photons combined. You want to do 1/2. Okay, so you're going to do 1/2 on both sides, right? In other words, you do 1/2 times the mass is 2 multiplied by 9.11 times 10 to the power negative 31. That's the mass of electron or the positron, same thing, times c squared. Don't forget the squared here. Common mistake. Okay, and you realize the 2's can be cancelled out, right? 1/2 and 2, they cancel out. And so the answer you're going to get, put it in the calculator, you should get, yeah, yeah, you should get like 0.51 mega electron volts. But by the way, that's like a corrected value because you're going to get in joules first, right? You're going to get in joules and you convert whatever you got here, right, into mega electron volts. Okay, so yeah, let's do the calculation right now. So I'll show you guys how that's being done. Figure out the answer here. This is how many joules we have. Okay, you can use some shortcuts. I'm sure the schools has taught you some sort of shortcut to convert joules into mega electron volts. If they haven't done so, a simple trick is to simply divide by 1.6 by 10 to the power negative 19 first, right? That converts to electron volts. If you do that, 1.6, okay. This is the value you get. And if you divide it by 10 to the power of 6, which is mega, you get 0.51-ish. That is the answer. Okay, so here we go. That's B, not C. Many people would choose C because they forgot to divide by 2. Right, that could be the reason. Alrighty, let's carry on. So oh, we're in section B right now. Fabulous. Section B. Finally, we get to the point where most of the points lie. So you do want to spend more time in fact, section B compared to section A, because section A, only 13 marks. Only 13 marks, right? You're not going to get much from it. But for section B, it's a lot more marks, right? So it's worth you to invest some time in doing the questions in section B. Let's go over the questions, okay? Now, one trick I teach students all the time is you gotta draw a diagram. It takes 30 seconds to a minute to draw a diagram, but that's the insurance you bought for yourself because that's gonna guarantee you're gonna get things right, okay? So I would draw a standing wave, fixed at both ends, and you're gonna draw the lowest frequency of vibration, which is one single loop, like this. N equals to 1. That's the lowest resonant frequency possible. So if this formula is not given, by the way, you should put this down in the cheat sheet. NV over 2L, right? In this case, N is 1. So 1 times V, 60, divided by 2 times L. that's 6, and you should get the F1 equals to 5 hertz. Okay. Some students may prefer finding the wavelength first, right? And then find the frequency. Look, it's fine. You can do 2L over N, find a wavelength, and you find a frequency. Which, yeah, I can demonstrate how you're going to find a wavelength. If we have a second lowest frequency of resonance, second lowest, okay, lowest is 1 loop, second lowest 1, and 2 loops in total, right? So N equals to 2 would be the situation, and you can apply the formula. 2 times the length divided by 2, right? That's 6 meters, 6 meters, okay? So put the answer in the box, don't forget that, all right? There you go. So that's how you use the formula to figure out the answer. Part C. On the string below, draw the standing wave envelope. Okay. Now it says envelope, which means you're going to draw the envelope. Don't just draw one strand. That's not going to work. Okay. When we have the third lowest frequency resonance, third lowest, N equals to 3. Okay. That is the third lowest frequency resonance. Fix at both ends. You can do that. Look, here's a trick. I know there'll be 3 loops, 1, 2, 3. So I cut it into 3 parts, right? So you can draw 2 notes right here to help you to draw this line. I hope I can nail this in one go. Not too shabby. Okay, I give myself a pass. Now, don't forget to add this line, a dotted line to show it is an envelope. Try to be identical for all 3 loops. Okay, try to be identical for all of them. So there are 2 marks, 1 mark for the solid line, 1 mark for the dotted line. Okay. Now, I believe usually VCE is quite they're quite reserved in terms of giving marks. So this could be a 1-mark question, which means if you miss out the dotted lines, you don't get anything. So be careful in that regard. Lastly, explanation question. This is one important part in Unit 4 physics, because a lot of question now, it's not really calculations, but to explain a concept, right? To elaborate on ideas. And one thing I see many students get wrong is they spend too much time in writing paragraphs and paragraphs and paragraphs, and they not even get to the point. Okay, so they spend a lot of time in it, and they get 0 points, for these sections. So I want to show you guys a trick that we use all the time is to use the technique of dot points. Okay, answer in dot points. Each point is one idea that worth 1 mark. Okay. How do we explain that? First of all, standing waves. They are progressive transverse waves. Okay. Traveling, you should mention they're traveling at the first place in opposite directions. Now, and they are reflected. They are reflected at the fixed ends of the string. Okay, so we got 2 waves, they're traveling in opposite directions, and by the time they hit, the fixed ends, they bounce back, right? And this bouncing back, or should I say, the incident and reflected waves undergo superposition. Look, this is a model answer, but you don't need to write every single word like this, right? You can use it your own sort of language to explain what's going on. But I'll highlight some keywords afterwards. We'll break down the answer together. Interfering constructively and destructively. To form alternating notes and anti-notes. You can see we got very comprehensive answers. Just to make sure you get every word you need in your response. Okay, thus forming a standing wave. Now, at the start, I mentioned I will give some insights for teachers or markers. How do they mark the exam? So when I mark the exam, something I would see is a handful of keywords, right? To check to see if you understand the physics behind that, right? You must speak in the language of physics. You must use scientific knowledge or language to elaborate on the concepts. So for example, you're going to talk about opposite direction, transverse wave traveling, the reflected. You must mention a superposition. That's one key phenomenon that's happening in this case. And different types of interference, and you can form some notes and anti-notes, and therefore forming a standing wave, right? So I want to see you incorporate those keywords in your response as we go, all right? So make sure your response is filled with these languages, right? With these keywords presented in a logical way, right? Preferably 2 dot points, right? 2 ideas, so you can impress the markers by doing so. All right, that is the trick I want to teach you guys. Okay, lastly, for part E, will a standing wave form for this frequency? Now, sometimes it may not, right? Because it's a quantized phenomenon. Only certain frequencies would form a standing wave for a particular string. That depends on the length. That depends on the nature of the string itself, like the tension, etc. Right. So you're going to be careful in this scenario. Okay. Now, if a standing wave could form, F is mv over 2L, right? And then, look, we don't know what n is. N could be any number, okay? But for a standing wave to form, n must be an integer. Integer means 1, 2, 3, 4, 5, so on and so forth, okay? So our job is to put all the values in, and then we figure out if n is an integer or not. If it is, cool, a standing wave could form. If it's not, no standing wave at all. All right, so 7.5 hertz n times the speed, which I believe is given as 60, divided by 2 times 6. And you should get n as 1.5. Okay, now you reason why a standing wave can't form, right? Because n must be an integer, right? So that's one mark on the left-hand side. Another mark is your explanation. N must be an integer, okay, for a standing wave to form. Now it's not, so a standing wave can't form because n is not integer, right? So you must mention a standing wave can't form. What does not form, right? Can't, wouldn't form as n is not an integer. Okay, there you go. You can divide the workspace into 2 parts, right? One for the calculation, the other for explanation. If you present the ideas clearly, your marker will deeply appreciate you, trust me. Okay, so yeah, you can even divide the areas by yourself. You can just write a line and do that. Make sure you don't write out of bounds. You write it within the paper that's being marked. And that's the first question, folks. So question 2. Oh, good luck. We got a diagram for this one. So let's take a look. For this question, a diffraction experiment. Okay. Now, once again, guys, diffraction, every single time you do diffraction, please do this. This will help a lot. And you see quick improvements as you start writing the relevant formulas pertaining to a particular concept. Okay, so please start getting the habit. Okay, is when you see a question, you can identify the relevant topics very quickly. Okay, look, I've been studying and teaching or studying how to teach physics for more than 10 years, right? So I can do this naturally. It has to be trained, and it takes time to train that instinct. Okay, so don't expect yourself to do it in one go, right? And don't be frustrated if you can't. It takes time to master the skill. Question A, will a diffraction pattern be observable? Explain your answer. This is crucial. Okay, in fact, in the last year's examination, 2024, there's one similar question in this way, and it's been discussed, amongst the markers that they realize students have understood something wrong fundamentally. Okay, and here I am to explain what that is and to give the right understanding to the public. Okay, so again, speaking on behalf of myself, right? It's not official VCA advice, and just please take that as our company's advice, right? To do well. It is observable, in fact, and your job is to prove why that is the case. All right. I'm sure most of you have heard of, okay, if this diffraction is less than 1, it is not observable. I'm sure many of you heard of that, but please abandon this idea from now on. Okay, what you should compare is the order of magnitude between lambda, wavelength, and the width. Okay, if they share the same order of magnitude, even this fraction is less than 1, right? It is still observable. Okay, so let's check, right? We're given a frequency, right? It's light, so we can use these two ideas to figure out lambda, which you can do it very quickly. So lambda is c over f, which you write down 3 to the times 10 to the power of x divided by 6, 10 to the power of 14. And you should get like 5 times 10 to the power of negative 7 meters. All right. Now 0.6 micrometers. This is the width. All right. So W is 0.6 times 10 to the power of negative 6, which is 6 times 10 to the power of negative 7 meters. Okay. Now, you must explain. So this is insufficient, right? Does this work out, even though it's pretty impressive already, it is insufficient. Okay, I'll put the yes over here and put the workings over there. Because lambda and width share the same order of magnitude. Now, of course, right, if you have like a greater order of magnitude for the lambda, right, this fraction should be greater, right, should be greater than 10, greater than 1. That's more like visible. It's more significant, the fraction, comparatively. But if you have like the same order of magnitude, it is still a visible, observable diffraction pattern. All right. So please change your approach from now on. When you see questions like that, all right, you compare the order of magnitudes. All right, rather than thinking, oh, is this fraction greater than 1, less than 1? Okay, stop thinking in that way. All right. Part B, state and explain the amount, 2 ways in which the amount of diffraction can be decreased. Okay, look, guys, this is why we write this equation down. On every equation is a proportionality concept, right? There are 2 variables, so 2 ideas, 2 ways. You fix or tamper with the 2 variables. That's that, right? If you want to reduce it, right, decrease, you want to reduce the fraction, you can either reduce the wavelength or increase the width, of the slit. Okay, so 2 things you can say. You can say decreasing the wavelength, right? Or you can say increase the frequency, given that it's traveling in the same medium, right? So that should be corresponding, right? Increasing the frequency. The second point you can say is to you're going to state and explain. So you have to explain as well, right? So you can't just state the change, but you're going to explain why. But in that case, you can simply say in words, right? Or you quote the equation, diffraction is proportional, directly proportional to lambda, and diffraction is inversely proportional to the width. Okay, so you can say increasing the gap width also decreases the degree of diffraction. Okay, so yeah, You can put these together, right? That's 1 point. You can put the second point as how these two are mathematically correlated, all right? Or how these variables are correlated in a way. That's number 2. Question 3. Okay, classic setup. Performing Young-Stubble's experiment as shown below. So let me check. All right, you want to find, okay, distance between the slits are given. So I'll hunt for these keywords, right, between the slits. So that's D. It's 50 micrometers. I would change the unit straight away before I forget. Okay, distance between the slit and the screen is 1 meter. Love it. L is 1 meter. Fabulous. Right, easy units and easy values. Okay, explain how this experiment supports the wave model of light. Now, it's a great hint in the picture that's given to you, right? You can see the interlacing patterns, black and white, black and white. That is the famous interference pattern, okay? So you must talk about when monochromatic light, which means one frequency of light was passed through the double slit, you observed an alternating series of bright and dark bands. Don't say black and white, because printing is black and white, but the color, look, it could not even be like visible light, right? They could use X-ray, they could use infrared, and they demonstrate the same effect, right? By measuring intensity, they can figure out which places are brighter or more intense. Okay, so try to use the words bright and dark bands, right, to illustrate that. But usually they should use visible light because you want to see the result. Okay, now that, okay, say was produced corresponding to constructive and destructive interference. Respectively. Now, this is a very lengthy first stop point, okay? It's a very lengthy one. I can show you guys the keywords and you can simplify it in your own, but I just want to show the complete picture, right? And you can refine the answer as you go, but don't miss out the keywords, okay? Next thing, you must state the fact that interference is a wave, unique to wave phenomenon, okay? Particles, they don't do interference, okay? And so the experiment supports the wave model of light. Keywords. By observing the bright and dark fringes, or those bands, all right, this is the observation part, okay? And you try to explain, what does that imply, okay? It implies that there's interference happening, because if it doesn't happen, all you're going to see is 2 bright bands, on the screen, if there's no interference whatsoever, right? But now you're observing this interference interlacing pattern, bright and dark, that implies there must be interference, because that's constructive and destructive to form these bands. And the next point you're going to talk about is that interference is a wave unique to wave phenomenon, and therefore the experiment supports the wave model of light, not the particle one. Okay, so that's 2 marks. All right, 2 marks in there. Part B is calculations. So something we did before, as we read the question, will pay off. Okay, D's given, L's given, right? And all we need to do is to see what's another thing that's given, right? 2 adjacent bright fringes is 1.18 centimeters. immediately put down delta x is 1.18 times 10 to the power negative 2 meters. Okay. And so when you find a path difference, right, you're going to think about, oh, it's asking path difference. So it's pretty tricky in this one. Actually, I'll divide the workspace into two parts because I can foresee there'll be 1 and 2 separate calculations that's to be done. Okay. Now the first one is path difference, right? Path difference is always related to wavelength. So I don't see the wavelength. I have to find a wavelength first before I do the path difference. So let's think about it. You can do reverse engineering, which I'll show how to do it, right? You can see point P. Okay. If C is 0 lambdas, the next one is like 0.5 lambdas of path difference. At point P is 1.5 lambdas. And like this is 1 lambda, so on and so forth. Okay. So path difference is 1.5 lambdas. You can write this down first because you unload some sort of thinking onto the piece of paper. And then you think to yourself, okay, we now need the lambda. We now need the wavelength. Where do I get that? Look, the only equation that we have, which includes all the other distances given in this question, is nothing but the fringe separation. Delta x is lambda L over D. That's the fringe separation equation. So you just sub all the values in, right? 1.18 times 10 to the power of negative 2 equals to the lambda, which we're going to find, times L. Oh, that's 1. Perfect. Perfect. Divided by D, and D is nothing but 50 times 10 to the power negative 6. You should find this as 5.90 times 10 to the negative 7 meters. And you can sub it in to the next part of the question. Now, notice that every time I start from an equation, I wrote the equation, I wrote a substitution. Even though in VCE, this is the part where you score, right? You have 1 mark for correct substitution. It is also important for you to show to the markers, okay, I knew the equation, and hey, I sub everything in the right place. So this step technically doesn't worth any marks, but I would always include it, okay, for the sake of clarity, and it's for you to put the values in the right spots. So don't forget, every single thing I wrote here is essential. Put the value of lambda in. You can add the brackets if you like to. That's fine, doesn't matter, it's multiplication. PD is 8.85 times 10 to the power negative 7 meters. Job's done? Not exactly. Check the units. Nanometers. Change it to nanometers by dividing by 10 to the power of negative 9. Okay, so that should be 885 nanometers. There you go. 3 sigmas. Okay. So when you divide a workspace into 2 parts, oh, perfect representation. As a teacher, I much prefer this way of presenting the answers than having like a bunch of random thoughts and scribble for me to treasure 100 answers. This is way preferable. Okay, so please do the right thing. All right, do it for me. Move on to part C. Okay, another point, so that's not the previous one. We have this notation. It is further from S1 than S2 by a certain value. What does that mean, right? If you say it is further from S1 to S2 by a certain value, does that mean it's a path difference? Okay, so actually this number is a fancy way to say the path difference is 1,180 nanometers. It is to the right, not to the left of point C, so you should write something in this region. Indicate where the point is by putting the letter X. Now, the thing is, you don't know if that's constructive or destructive. Is it bright or dark band? You have no idea. All you know is the path difference. All right. So how about we put it this way? PD is like a random number X multiplied by lambda. Okay. Look, if X is equal to 0, 1, 2, 3, okay, that's constructive. Okay. If X is equal to 0.5, 1.5, 2.5, etc., that would be destructive. Our job here is to see what does X correspond to, and then we can move on from there. Okay, put down this value, and here's the tip. You can in fact use the same unit. You can use nanometers, because right, that's nanometers for PD, path difference. This is nanometers for wavelength, and X is just like a factor. It's a number without any units. Okay, so as long as we have the same unit, it is fine. 800, no, sorry, not 800. That was a previous answer. Don't use that one. Use the wavelength. That should be 590 nanometers for the wavelength. All right. So yeah, we established this at part B before. Okay, you can see here. Right, this is like 590 nanometers. You can do that. That makes the mathematics so much easier, right? X equals to 2. You multiply by 2. All right. In other words, you must show your working, right? So X equals to 2. You can even add that, right? PD equals to 2 lambda. So therefore, it is constructive. Look, if you were to explain, that's how you do it. Okay. That's 0 lambdas for path difference. That's 1. That's 2 lambdas, which means X is right about this one here. Okay. And that is how you do questions like that. Lastly, very hard question, very hard one. You change the wavelength. Okay, you change the wavelength. And then there is now a bright band at point P. So point P was where? Okay, point P was there. Okay, that was the second dark band. That was point P. But now when you change the wavelength, everything changes. Everything changes. Okay, except for one thing. The color of the band may change. Is it bright or is it dark? It could be different interference type. It could be constructive or destructive. But then the only thing that remains the same would be the path difference, right? So PD is still 885 nanometers. Why is that the same? Because, hey, you can have different patterns, but then the distance from that particular point on the screen to the slits is not changed, right? It remains the same, okay? So please bear this in mind, right? Despite you change the wavelength, you change the frequency, doesn't matter. The path difference at point P, it is still 885 nanometers. And we're going to go from there. Okay, how do we get the new wavelength? We'll give it another clue. It is the third bright band to the left of C, okay, which is not including C itself. Okay, I used another color. Okay, for D, is a blue, right? Not blue, let's use another one. This is purple. Okay, third bright band to the left of C, not including one. That's the first one, second one, that's the third one, okay, right here. So 0 lambdas, 1 lambda, 2 lambdas, 3 lambdas, okay, which means at this point, okay, look, please don't take this as the same diagram as before, because look, the width between the fringes could be changed, okay? So I'm just assuming, look, if we have a pattern like this, right, it would be the third bright band from point C, disregarding that. So there'll be 3 lambda as the path difference. That's the point I want to deliver, okay? Not exactly, because the pattern has changed, right? So not exactly here, but it is 3 lambdas. In other words, 3 times lambda is 885 nanometers. Okay, you divide by 3, and you're going to get lambda as 295 nanometers. There you go. All right, so that's part D. Question 4. This one, 70 marks. Don't let this scare you. Okay, don't let this scare you. Okay, 70 marks is a lot of marks. Okay, the question is asking you to plot a frequency against stopping voltage graph. Okay, so please take a look at this one, okay, times 10 to the power 14. So all the values you're going to use, all right, you should adjust it to the corresponding value of 10 to the power 14. But look, if you just plot 10 times 10 to the power 14 every single time, that's going to be a waste of your time. Okay, so here's what we're going to do. Put stopping voltage against, all right, you can say Vs is a stopping voltage, V against frequency. So remember to draw all these labels. Frequency F in units of hertz. Now, not just any hertz, but if I were to change it, I would say times 10 to the power 14 hertz. Okay. 0, 1, 2, 3. You can be more precise. You can put like 3.0, etc. That's a better way to graph it. It fits the sig figs to the data that gave you. Okay. 2.0, 4.0, so on and so forth. How do I know intervals of 2? You just check, right? We have the maximum to be 14 times 10 to the power 14. So yeah, that's fine. That's inclusive to the range that we have. And you just plot the data in, right? So I'm not going to demonstrate very clearly how to do it, right? But basically for the first one, stopping voltage 0.5, you draw a horizontal line here, 8.3, somewhat about there, and you just put a point here. Okay. I like to use crosses because that pinpoints exactly where the point should be. Here you go. That's roughly, again, just roughly here and there. The last step we're going to do is to draw a line of best fit. Use a ruler. Okay. Look, when you draw the line of best fit, several things to pay attention to. Okay. You try to average the points. There is absolutely no need to go through every single point. It's not required. Okay. But you should have the similar number of points above and below this line because the mine one is not that good. Please, please, please do not pass the line from the start to the final point like this. This is not how you draw the best fit line. Okay, I don't know why some students, they think that's the way to do it, but you're actually taking an average among all the points. In some cases, if those points are outliers, you're not drawing the best fit. Okay, so I'm gonna try to find out like an average, not a curve, a straight line. Let me take a bit of practice. I think that's easier to be done if you have like an actual ruler than doing this online, but hey, here you go. Can't make excuses. I can adjust it a bit higher. And one thing you should be considering doing is to extrapolate this, right? So we're not out of bounds, keep it in, but you should extrapolate this line to the y-axis. Okay, so because I can't draw dotted lines, I just have to do this and do such a primitive way to erase the gaps. So I'll just show you how that's done. Yeah, there you go. Okay, just roughly. Okay, I believe my line is not perfect, right? It's never perfect. Yeah, I'll be honest to myself, roughly here. Okay, which should be different from our proposed solution. Okay, identify one important control variable for the experiment. Okay, so that line's done. Okay, by the way, let me just talk about the marks allocation. 1 mark for the S labels and units, 1 mark for the scale, 1 mark for data points, and 1 mark for the line of best fit. Okay, so 4 marks in total. Part B, identify one important control variable for the experiment and explain why this variable should be controlled. Okay, so in here, right, we do the experiment. Look, we are changing the frequency, and hence the stopping voltage is changing. Okay, so one thing we should be not changing, should not be changing, is the calcium metal plate. You know, the plate itself, the thickness, the material shouldn't be altered at all. Okay, so we could say the type of metal plate, calcium, should be controlled. right? And that is to ensure, why is that, right? Explain why, right? That is to ensure that the work function, sorry, the work function is the same. Okay, as this work function can affect the maximum kinetic energy of the photoelectrons. Try to use the full name instead of like EK max. All right. And you can say of the photoelectrons to be even more specific. And thus stopping voltage. Right. Work function should be a constant. Okay. So past Cs, they use the graph to estimate the work function. Usually they give like a range, right? So use the graph to estimate the work function. Must use the graph. You can't just calculate it. Please don't do that. You must refer to the graph. Include units for your answers. Work function and threshold frequency. So look, I'll be honest to the graph I've drawn. That's roughly 3.2, 3.3-ish. Usually they got a range of acceptance. Okay, so as long as you fall within the range, that is fine. Okay, that is fine. All right, so here, look, I'm just going to use the answer we proposed, in the solutions. So actually, no, I'll just use the ones I have here. Okay, that's like negative 3.3 or just 3.3 for the work function in the unit of V. So look, if this says V, all right, the shortcut is if this becomes, if you want to convert this into like energy, that's E equals to QV, yeah? Right. You can do it in joules by putting in 1.6 times 10 to the power negative 19 for the charge. But if it's want to do it electron volts, it's simply put Q equals to 1. Right. So just multiply the voltage by 1. All right. In other words, whatever voltage that's shown on the y-axis, the interception, right, the intercept, you can say it's electron volts. That is the shortcut. Okay. What about the threshold frequency? Okay. Threshold frequency is the frequency, the minimum frequency for photoelectrons to start emerging, to start emitting. Okay. So it is actually this intercept right here, because when we go beyond this frequency, there is, there's some electrons moving, and that requires a stopping voltage. All right. So in my case, that's about 7.1, 7.2. Don't forget times 10 to the power 14 hertz. Okay, you can see that right here, right here. Don't forget that. Next, use the graph to find the value of Planck's constant. Include the unit in your answer. Okay, now if you think about this graph right here, and you draw this EK max equals to HF minus the work function. Okay, now EK max can also be expressed by QV stopping voltage. Okay, well, if you think about Y equals to mx plus b, plus c, that's how I did it. You can align it, right? If you plot like Y and then X is the frequency, the intercept would be like C would be, the minus negative work function, which you just did, right? That's 3.3, which is negative. So negative 3.3 is minus C, or minus the work function. But then the gradient of this graph would be Planck's constant. So it should be a constant. And so you should use the gradient to figure out what the Planck constant is. All right. Now, you must choose not the points, but the line of best fit those not data points. You must choose from the line of best fit when you do this plot. Okay. Choose 2 points right here. Look, ideally you should have more intervals, so you can pick like better points to do the estimation. I'm just making things up, right? Let's say the graph we had like 3.3. What else do we have? Let's not use 3.3. That's not a good one. Okay. Actually, 3.3 is fine. It's fine because it's not the data points, but it's the line, right? So I can use this, and you can use somewhat like here, right? Like this one. So to figure out, the gradients for the Planck's constant, you can do that, right? You can do that. For simple reasons, I'm just gonna use the model answer one again, just demonstrate how that's being done. But you guys may have your own answers. Okay, that's electron volts, by the way, because you use EV for the vertical axis. As I said, right, it's showing voltage, right, voltage, but you convert into electron volts, you times it by one electron. Okay, so here you go. And let's assume that, the horizontal, the difference, right, the rise over run, it's 14 minus 7 times 10 to the power 14. Then the Planck's constant should be somewhat like 4.3 in this case. Again, everyone's going to be getting different answers, but just trying to demonstrate the method. Don't forget the units because it says include a unit in your answer. Okay, many people will forget this part, right? It's the multiply by 10 to the power 14. Okay, like here. Okay, 2 more questions to go for this question. This big one. If the power rating is 40 megawatts, find the total number of photons per second, and which is quite similar to the equation we talked about, right? And you can actually write this down that P equals to NHF, right, over the time. Okay. Let me see. If you use this understanding, and actually just put it here, right? P is E over T, which is NHF over time, because it's number of electrons times each of them has HF amounts of energy divided by time. Frequency can be expressed by, or expressed in, C over lambda, like so. All right. And so let me check the number of photons, right? So hitting per second. All right, so the way you can do it is to put P as 40 times 10 to the power of negative 3. Let me change it to red. That's equal to N times the Planck's constant. In this case, we will use the 6.671. Oh, hang on. You say you may use the theoretical value. You may use the one above. You may use the theoretical value. And look, we use the theoretical value. 6.63, not 7, 6.63 times that, times the speed of light, divided by the wavelength, 610 times 10 to the power negative 3, sorry, negative 9, and then you multiply by time, which is 1 second, because it says per second, right, per second, and you solve for n. That should be 1.2 times 10 to the power 17 photons. Okay, just algebra. But the most important thing is this equation right here. It's not given to you directly, but that's an important conceptual understanding that you should have. All right. Next one, find the maximum speed. So whenever you think about speed, relate to kinetic energy straight away. Okay, maximum means has to do with EK max, not any sort of energy, but the maximum kinetic energy. Equals to HF minus phi. And 1/2 mv squared is HF minus the work function. So look, this is going to be a long equation. H, you can use the theoretical value. Make sure you use the one in joules. Frequency is given 12.0 times 10 to the power 14 minus the work function. The the work function has to be the one converted into joules, of course. So you set something like 3.3. You're going to multiply this by 1.6, 10 to the power negative 19. Okay, so that should give you 8.3 times 10 to the power 5. If you get any value that's greater than that, chances are you forgot to do the square root because you got like v squared over here. Okay, so you may forget to do the square root as you figure out what v is. Yeah, so the order of magnitude should be close to like 4 to 6, right? 10 to the power 4 to 6. That's roughly how fast, those electrons are moving. We're almost there. Okay, so we got a couple more questions to go. Part G, outline the observations. All right. So I'll just give you one example. There are many things you can talk about. So one example is like the threshold frequency. The existence of a threshold frequency of photo emission. So when you have emissions, it doesn't work with any frequency. It has like a threshold. Minimal has to be this one. Otherwise, nothing happens. Which model, explain how it supports the particle models. When you break it down, outline the observation as 1 mark. Explain how it supports the particle model, that's the 2nd mark. And how this does not support the wave model or going against it. That's the 3rd mark right here. Okay. Particle model predicts that the energy of each photon is dependent on its frequency. Okay, so you can even quote the equation, E is HF. Add the line, since the energy transferred must be greater than the work function for photo emission. Okay, sorry, a bit cranky towards the end. The frequency must exist, all right? Or I can say of the incident photons must exceed a threshold. Okay. That is how it supports the particle model of understanding, because particle model predicts each photon has an energy E equals HF, right? If there's not enough frequency, it implies there's not enough energy, right, to overcome the work function. So nothing's gonna happen. All right, nothing's gonna happen. And that actually ties closely to the other theory that there's no time delay, because it's like one photon collided with one electron, and that is like an instantaneous emission, which means that for the electrons, they can't store the energy because it's 1-to-1, one particle to another particle, such a collision. You kind of many to one. That's not the case. It's not like wave where you can accumulate the energy. So even it's very low frequency, after some time, you got enough energy to be shot out. That's not the case. Okay. And you can also add, it's actually quite comprehensive, the way we give our answers. This did not support the wave model. You're going to explain why, right? So which predicts that the measure of a wave's energy is its amplitude, not frequency. Okay, so the prediction by the wave model is that light of all frequencies should be able to cause a photon emission, right? To lead to the emission of photoelectrons. But of course, that's not the case, right? That's the prediction from the wave perspective, but that is not the case, right? And of course, it's given that if the intensity is high enough, right? So if you shine it for a long period of time, right, extensive period of time, that's the wave's prediction. But in reality, nothing like that happens. I want to make this very clear. Okay, so look, the way we explain it is very comprehensive. We give it a lot of information. You can see I write paragraphs and paragraphs and paragraphs, but we don't need to do that in VCE. Please do not do that. This is for your understanding. That's why I'm doing this in very deep and detailed response. In your understanding, what you should do is to figure out the main points, which I'll show you. For example, first thing, threshold frequency exists for photo emission. That's the first point. This supports the particle model because you must talk about E equals HF, right? Energy depends on frequency. All right. And so you must have an energy greater than the work function so that the frequency must exceed the threshold frequency. That is the idea. All right. Now, so this does not support the wave model. Okay. Wave model, you can say wave model predicts that the wave's energy is its amplitude or not frequency. Okay. You must mention light of all frequencies should be able to cause photon emission. That is the main point for the second one. All right. And please note that other answers are possible. There are many other possible responses. For example, a negligible time delay before photon emission. Okay. It is not instant. I mean, nothing's instant, right? Even it's like the light, the collision takes time, a little bit of time, but it's negligible time delay. There's also stopping voltage and frequency dependence. All right. And you can also say independence of the stopping voltage and the intensity, right? Because intensity in the language of a particle model, it refers to the number of photons. Has nothing to do with energy, once again, but the wave interpret intensity as energy. All right. So these are the main things you should point out in your response. Okay. Question 5. It's a classic. Almost every year we have a similar question like this. There are two circles, okay? And I've seen this many, many times, all right? So I can recognize one is the X-ray, one's the electron, okay? I can't really tell which is which, all right? In this case, X-rays on the left, electrons on the right. But you can tell they're very similar, all right? So you may have guessed, this is to show that electrons behave like a wave. Sometimes they have the properties of wave and particle. Okay, so the X-ray diffraction and the electron diffraction is a famous experiment. Let's check the scenario. Emily and Harry discussing the patterns. Emily says, because the patterns are similar, they must have same momentum and energy. Whereas Harry disagrees. He simply argues that electrons have the same momentum, but different energies. Who's correct? Now, Harry, in this case, is correct. Why is that? Okay. You can relate to the formulas, all right, which I'll try to explain with the formulas. The key formula here is the photon momentum, right? P is h over lambda. And also the equation, the de Broglie wavelength. I hope again I don't butcher his name. All right. For electrons, it depends on the momentum, right? So m times v. And you can notice that the similarity between these two equations, right? If one thing you can see from the pattern is they share the same wavelength. The X-ray and the electron wavelength is the same. They're the same. Okay. If we plug into the equation, that the P, the momentum derived from the equations, should also be identical, right? But energy is not. Okay. Because some of you may say, Eric, look, for energy, let's say for electrons, I can use energy is P squared over 2m to figure out the energy. But hey guys, you can't use the same equation for a massless photon. That's not how it works. For photons, E is hf, right? Or you can say E is hc over lambda. When you do the maths, you figure out these two are not exactly the same. Okay, but you want to explain clearly who's correct or who's not. Okay, so you can say the amount of diffraction depends on the wavelength and crystal spacing. Okay, now you can say since crystal spacing is the same, in both setup, so therefore X-ray and electrons must have the same wavelength. So this one is like arguing to the fundamentals, like why do they share the same wavelength? Because look at the diffraction pattern, right? Look at the degree of diffraction, right? Once again, this relationship comes out. If the width's the same, the diffraction degree is the same, right? That the wavelength should be the same, right? Share amongst the X-ray and electrons. Okay, now last point. You can say, quote another equation, wavelength is related to momentum, or is related to momentum. So, or you can say that, you can quote the energy equations as well if you want to take a step further. But yeah, you're trying to explain, so the X-rays and electrons must have the same momentum, but not the same energy. All right, at the corner, but not space. Here you go. All right. Last question for part B. If the energy is found to be 256 electron volts, okay, calculate the speed of the electrons to create the diffraction pattern on the right. So you're given one piece of information off the left, which is the X-ray diffraction pattern. You try to find a way to link it to the electron's diffraction pattern. Okay, and the linkage could be momentum, could be the wavelength. So either one would work in this case. All right. Let's take a look. If we were to do this question, okay, so we're given the electron volts, that's energy, right? So energy, let's think about X-rays. Okay, energy, what do we have? HF, you can say also HC over lambda, and you go, aha, lambda, right? Lambda is the link that we're trying to find, okay? And you think about, once we get the lambda, how do we get the speed of those electrons? Lambda and speed, okay? Now, one common concept trap is to think about 1/2 mv squared. and you say energies are equal, but energy is not equal. Please remember that energy is not equal. Okay, lambda wavelength is. Okay, so wavelength is P, sorry, H over P, which is H over mv. And there you go. Once you find the lambda, equate the X-ray and the electron's lambda, the wavelength the same, and then you can find V. That is the logic. Okay, so let's do it. E of the X-ray is Hc over lambda. So 256, you can use the electron volts. If you use the Planck's constant, it's 4.14 times 10 to the negative 15, times it by 3 times 10 to the power of 8, divided by the wavelength of X-ray. Okay, so X-ray is 4.85 times 10 to the power of negative 9 meters, and you can have this equating to the electron wavelength. Pro tip, divide the workspace. Divide the workspace. Because we move on to the second phase, right? The second phase is this equation, right? So 4.85 times 10 to the power of negative 9 is the wavelength. Now, this is the case you're going to use another Planck's constant, another value, because you want to have it as meters per second, right? So you should use the one in joules. And so H is like 6.63, 10 to the negative 34, divided electron mass times V. So V should get something, again, 10 to the power 5 is the very common order of magnitude. It may not always be the case, but it's a good way to check your answers to make sure that makes sense. Excuse me. There you go. So you present your work in a very logical way. Lastly, describe another experiment that demonstrates the wave-particle duality of matter. There are many experiments you can say. My personal favorite is electron double slit. Okay, so it's like double slit experiment, but electron version. Okay, so you can say that the electron double slit experiment. Firing electrons at a double slit. Like this is basically how that's done. One at a time. That's point number one. Number two. Okay. Over time, an interference pattern is formed. With alternating regions. Now we say a high and low intensity. Now you must imply, you must say, what does that imply, right? It's indicating, right, that individual electrons exhibit these wave-like behavior, because anything with interference is wave-like. And can interfere with themselves. Okay. The trick is, this is not the whole experiment. Okay, so the original story goes like this. They put detectors now. They put detectors. Okay, so when Eric, you say, those electrons, they pass through both slits at the same time, and therefore interferencing with each other, right? They interfere with each other, right? Interferencing is not a word, I guess. Interfere with each other. Okay. Now I want to see, right? I want actually put detectors on the slits and see which gate they pass through. Maybe both at the same time, right? If I get both detectors registered, okay, they pass through both slits at the same time. Interestingly, Okay, when the detectors are add on to that. However, right, if electrons are observed, so we try to observe the situation as they pass through the slits. What happens is two distinct bright bands are produced. Maybe not bright bands, let's just say two distinct bands, because they're just electrons and they're just the intensity of registering, the intensity they registered, two bands are produced, okay, rather than the interference pattern. This is a particle behavior, particle-like behavior. So this shows wave-like and particle-like behavior. That's how you get the duality. Okay. Now the story goes like this: like if there's detection, you try to observe the system. People thought observing does not cause any interruptions or any changes to the nature of the system, but in fact, the idea of observing something is actually one way to mess with the system. Okay, it's actually one way to tamper with the system. So observation is not something neutral. When you try to observe something, you actually change how things manifest, right? In whatever nature is more dominant than the other. All right. So sometimes electrons behave as waves. It's more dominant, right? It's more observable. Sometimes particles. Okay. If you observe them, the particle nature takes over. It's more observable as a particle than as a wave. Okay. That's the wave particle duality and the nature of observation in quantum mechanics, in fact. All right. So guys, we've got two more questions to go. So let's do question 6. 5 marks. That's a much easier question to tackle. Okay, we're gonna find the missing energy value. Okay, so let's see. We got some sort of energy levels. Okay, classic question once again. Energy levels of an atom of gas. The excites them just enough to get through the first three levels. We know N level 2 is 4.3. Okay, so we're going to draw a diagram later on. We can use these knowledge that we talked about. Ionization is 8.6. Okay, cool. For 230 nanometers of wavelength, what is the corresponding energy? Okay, so once again, energy is hc lambda. All right, and that will be quite a straightforward question. If it's electron volts, oh, good news, right? We can use 4.14 times 10 to the power negative 15, and then 3 times 10 to the power 8 meters per second for speed of light, 230 nanometers. So you add the 10 to the power negative 9, right? And so E is going to be something like 5.4 electron volts, right? So include 5.4, complete the missing value in the table above, put that in, done. All right, the next thing, it's more challenging. We're going to draw a diagram and explain what's going on. Okay, so let's draw all the states and all the levels. So I'll draw the state like so. And you can see some details I'm doing here is that the gap between the states are getting closer, closer, and closer. So the last one is ionization level. Good. And the next thing we're going to draw transition lines. Okay. Let's see. All right. So let's take a look. Um. We not determine the energy levels for n equals to 3, n equals to 4. We knew for a fact that n equals to 1 is 0. Okay, so let's draw it, sketch it here. Right, 0.0 eV. N equals to 2 is 4.3. And the ionization level is 8.6. And we're trying to find the remaining 2. Okay, now what you want to do is to check. Okay, want to check. There's a 4.3 emission, which is the only one, here, right? That's 4.3. I will put it on the left-hand side. There's, of course, 8.6 somewhere, right? This should be somewhere here. From 8.6 to 4.3, this one is actually, say, 4.3 as well. But hang on, we don't do the infinity, right? We don't do the infinity ionization level. So it's maximum is 4, and we consider from 4 to drop to each of the levels, what do we get? Okay. We get these small intervals, which I believe is between 4, 3, and 2. Okay, so that's why we got some small intervals. That's why. We also got 5.4. So I can make a blunt assumption that this is like 5.4 electron volts. So we have this 5.4 transition from here to there. And see if that makes sense, right? Because between 3 and 2, this is 1.1 electron volts. So this one's also taken. That's done. That's done. That's done. We need to find something like 0.7 and 1.8. So let's try to add 0.7, right, to 5.4, and we get 6.1 electron volts. Okay, so the difference between here and there is 0.7, so that's taken as well. And between this one and that one, 6.1 and 4.3, that's exactly 1.8. Wow, fabulous. Okay, I think now we got all the data. Okay, I mean, there should be 4 to 1. That should be 6.1. That's not shown above, but that's not very important. Okay, so it's given limited data. Can you find can you find the remaining ones? Okay, so it's like a logical question. It's very challenging, I believe, without any experiences. And you can simply explain what I just talked about, okay, in words. Okay. The reasoning simply is to say that those energy differences must be corresponding to the ones in the table, and you use that as an inference, right, to derive the levels over there. All right, guys, last question. Question 7 is the last one to go. So 7 marks to wrap it up. Okay, this is a special relativity question. Okay, and many students are struggling with special relativity. I want to spend a little bit more time to dig deep into the question and show them some tips and tricks, right, of how to do this. All right. Scientists, those guys are usually stationary. Okay, so scientists perform an experiment that involves elementary particle. Let me highlight them as stationary objects. Okay, it says travels this many meters in a single line. Now, you want to find the lifetime in a scientist frame of reference. Okay, a lot of people would dig into the proper time, the measured time straight away, without rethinking what's given. You actually give a velocity, right? V is something all observers agree with. Sorry, the speed of light is something all observers agree with. Okay, and V is in this case 0.99 times the speed of light. Scientists, they measure the distance to be 7.56 times 10 to the power -5 meters. So based on these two pieces of information, look, I'm going to use black to write the answers now because red and blue are different observers. Right, you can use this equation to figure out the time, and nothing fancy. Just put those values in, except for the fact that you should have 0.99 times the speed of light, and that gives a very short duration, this many seconds. Okay, this is the lifetime of the particle. Keep that in mind. Next question. Calculate the distance that the particle travels in the laboratory. Okay. Now, when you read the question, you must be very clear about this distance. Is it a proper length or not a proper length that the question is asking? Okay, let's think about it. If it's like a distance between 2 points, okay, like this distance is stationary, right? Like if I'm talking about a dimension, let's say of a pen, right? The dimension of this pen is moving, all right? If it's moving, then the dimensions of a moving object is where the people move along with it would measure its proper length, right? Because in their frame of reference, like this pen is stationary, okay? Or in other words, you must have to share the same frame of reference as the thing you're measuring. So if you talk about distances in the lab, it's a stationary distance between 2 points, right? The scientists, those guys are stationary as well, right? They share the same frame of reference as what they're measuring. That would be the proper length. Okay, so this must be defined very clearly at the start, right? This is the proper length by the scientists. So L naught would be 7.56 times 10 to the power negative 15. You're trying to find L. That's the measured length by this moving object in the particle's frame of reference. Okay, now please divide the workspace into 2 parts. All right, we always have one part to find the Lorentz factor. I found this to be the most effective. You always have one thing to find the Lorentz factor. Once you get the Lorentz factor, you sub it in to the equation. Okay, the equation I can write it down first. That goes like this. Okay, because I found it's way easier to handle these mathematics if you split into 2 parts. All right, so Lorentz factor 1 divided by 0.99. Look, the shortcut is those c squares would be canceling out. So it's just 0.99 squared, right? And that should be very close to 7.1. Make sure you use the uncorrected value. You have the actual value saved in the calculator and put into the equation to solve. So 7.56 times 10 to the power negative 15 divided by 7.1. 1.1 times 10 to the power negative 5 meters. 2 seconds. Alrighty. Does that make sense? Think about it. The particle is moving. So it's kind of moving and I see everything's going towards it, right? Everything's going towards it. So the original length that scientists are stationary, they observed that it's a very long length, very long distance between 2 points. In a particle's perspective, it's all coming to that, right? That the views in a train carriage, this is all going towards them. This length is contracted. Okay, this is one concept we call the length contraction. It's measured by the moving particle for something that's, the measured length is contracted in that sense. All right, and that ties closely to part C, where to explain why the scientists will observe more particles at the end of the laboratory measuring range than the classical physics would expect. There are 2 ways to do it, okay? I will start from the length contraction concept. Please make sure you don't mix up the 2 explanations. You either do first one or you do the second one. You can't have both at the same time. Okay, first point. Let me use red for now. Scientists would observe more particles due to length contraction. Length contraction is the keyword. 1 mark. Why is that? In the particles frame of reference, the distance to the detector is contracted. When measured from the particles frame of reference. I mean, yeah, I think I said the same thing, so there's no need to say at the end. Okay, and so this is more important, right? This is what the physics tells you, right? It's, okay, it's contracted. Okay, so why do we register more particles? So therefore, or thus, if you want to save some ink, right? The particles have, in their point of view, all right, the particles will have a shorter distance to travel. Okay, so even though they kind of die out, there's a very short half-life for them. They're very unstable. They disintegrate to other particles, right? Um, there's more that can make to the end because it's like a shorter distance. Okay, um, so more particles would be able to reach the detector before decaying, compared to what we predicted in classical physics. Okay, that's good enough for 3 marks. Okay, now some of you may think in another way. Let's not illustrate in the question. I want to spend about a couple minutes to go through this very quickly. Okay, another point of view is that the scientist will expect. Look, I'm just not going to write. I'm just going to put down the keywords, right? Because you know how to format it. You can say time dilation. Okay, now this is do not in the particles frame of reference, like all the things we talked about, it's in the particles frame of reference. It is something in the particles frame of reference. But time dilation is something to do with the scientists, the stationary observers themselves in this scenario. Okay. Look, don't memorize it as time dilation is stationary, is moving. It depends. It depends. Okay. In this case, okay, the scientist would measure a longer half-life. Okay. So in the scientist frame of reference, okay, try not to write FOR, but I'm just explaining, so I can do that. But in the actual explanation, write down the full response. Okay, frame of reference. Particles half-life is dilated, right? Is dilated, which means they measure a greater value. It's long, more. It's not short-lived, but like a longer-lived. Okay, so fewer particles will decay. Similar logic, right? Fewer particles will decay, but for a very different reason and for a very different perspective. This is the fun part about relativity. Different people have different conclusions about things. Okay, scientists don't see the length contracted. It's the same length, right? Same marathon, but then they live longer to make it to the end. But the particles, they are short-lived, but then the distance they travel is like shrinked, right? It's like a shorter distance, contracted, so they can still make it to the end. All right. So to conclude, in both perspectives, the conclusion is the same, right? They detect more particles that speed chain or striking the detector, right? They can make it to the end, but for very different reasons. Okay, that is the fun for special relativity. Okay, so folks, this is the end of the question and answer book. And hopefully through this exercise, you got more insights into how to do the physics questions, as well as how people will mark it. Okay, you get some tips and tricks here and there. As I mentioned, how do we structure the answers? How do we ensure we get all the marks? We're not losing any marks with poor presentation. Okay, if you want to experience something more like this, okay, feel free to let us know. Reach out to us so we can support your physics learning journey. And yeah, all the best in your SAC preparation and in your VC preparation.